Okay, recording in progress. Let me hide the meeting controls. Oops. Okay. So good morning and happy Wednesday. Today, we will be talking about practical considerations. We'll be looking at demonstrations of the central limit theorem to convince you that all the stuff we had spoken about or discussed, it actually works, right? And then we'll also look at the analysis problem, which was question 9 on written exam number 1. And I'm still working on it. Many of them have gotten back. The place where it's taking 80% of my time is question 9. So we're going to talk about question 9. People have done well, which I'm very happy about. So congratulations. Question 9, there are about so far about 6 different ways people have done it. And so the time is in trying to make a fair evaluation over the 6 different ways or categories of ways people have done it. So I'm going to also show you today one way of doing it. And so this will be a solution, not the solution. The written part, I have the solution there as well as this particular Python solution specifically for question 9 that I thought would be valuable to go over. The smoke alarm kept going off last night, so I didn't get much sleep. So I'm a little bit exhausted, more so than usual. Okay, but before we begin, some administrative bits. The reading hasn't changed. You all know when Project 5 is due. We're going to have a second written exam. This will be easier than the first one. I don't do cumulative exams. This will be on the material after exam 1 up to um, uh, today, up to including today. And so the format for it will be more analytical, and I will provide you with a data set, nothing like the taxi data set, so not to worry, but I'll provide you with a data set, and then I will ask you a couple questions about that data set, and you'll do some analyses. Now, the questions, it'll probably be 2, maybe 3 questions, and what I'm looking for are your exercise as various parts of the data science process. Because it's the usual exam format for me, the questions won't be quite as involved as they otherwise would on a project, because you have a whole week to do a project, but 24 hours for written exam number 2. And so I recalced the semester last night, and we have 3.5 weeks left for the end of the semester. What remains after this exam number 2 is project number 6, one more project, and that will be purpose with helping you towards the final project. And the final project will be a comprehensive analysis on a problem, and I'll furnish a data set for you, and you'll do a comprehensive analysis, both posing questions as well as doing analyses, answering those questions you pose, and then the last part, making recommendations based on your findings from the data to kind of close the loop on this entire process. Once we're done with what's called estimation, max likelihood, and method of moments, we'll pivot to the extraction of insights, and we'll be doing a number of machine learning methods, talking about how they work, why they work, as well as various implementations in the Python scikit-learn API for these things. So we'll be doing classification, clustering, regression. We will be looking at ensemble methods, perhaps random forest this year, and if time permits, neural networks, but I'm not sure. Depends on where the pacing lies. Okay, any questions? No? All right. So also, please make sure you're doing the course evaluations. I take them very seriously, and feedback from students are reflected in this semester, even though I taught the same class first time here at Clark last semester. So I do take very seriously both your reflections as well as your course evaluations. And of course, if I don't get a minimum number of course um, evaluations, there we go, then they lock them and no one can see them in perpetuity. So I really hope that at least 60% of you would submit them. Please take the time to do that. Tell me what you liked, tell me what you didn't like, tell me what you learned, tell me what you'd like to learn, and all of the above. Okay. Any questions? Yes. That's a great question. I'd have to check. I think it's through Canvas, but I don't see the student interface, so I'm not sure where I'd find them. But I can find out and I can post it for you when I get back to office hours after today. Okay. All right. Any other questions? No. All right. Let's see. All right. Yes. So where we last? Oh yes. Shameless plugs. So I'll be teaching a course that I actually designed and brought to Clark to the department, DSCI 216 this fall. I taught it 2 years ago, my first semester here, fall of 2021. And the course is called Stochastic Computing. You'll probably see these flyers in the hallway, these cheesy ads. And it's purposed with how you build algorithms that allow you to make decisions from or about systems that traffic in uncertainty. And so we cover various concepts from probability and statistics. Some of the same concepts we cover here, but we give it a more advanced treatment. But our purpose is for describing uncertainty. So we look at various algorithms, techniques for prototyping systems, how you measure uncertainty. So that's simulation, forecasting error, more about that Kalman filter that I talked about when I talked about the normal distribution, and also the evaluation of systems that traffic in uncertainty. And so new for this fall, I'm hoping to include more elements of financial time series, because as I understand, the economics department looks at socio-political concerns, but not the computational finance aspects. And so it's open to anyone. The prerequisites are kind of hybrid this year. When I taught it in fall of 2021, DSCI 122, Mathematics of Data Science, didn't exist. In fact, that course was created because of stochastic computing, and that's listed as the formal prerequisite. I'll still sign overrides if people ask, depending, plus or minus. But what we're going to look at from that course is we're going to make use of tools from linear algebra, matrix decomposition, and stuff like that for a really important concept, feature selection. And we'll talk about that in this class, among other things. Question? I know one of the prerequisites is Calc 1 and mathematics of data science. And so the math part is important. I'll certainly cover some of it. So to answer your question, should you have taken calculus 2, you said? Okay. If you have not taken mathematics of data science, I'll still sign the override. And so this class this fall will be kind of a hybrid, because I expect there to be a population of students in the class who have not taken 122. Of course, I'll throw into that group those who are taking it at the same time, as well as those who have taken it. And so I'm still trying to figure out what that balance is. But I'll still sound the override if you haven't taken 122. If you have, great, but that only is one classroom full of students as a population, because I think it was being taught this semester I think it's for the first time this semester. Maybe it was taught last semester. I'd have to check. Did I answer your question? All right. Any other questions? No? All right. This other course, shameless plug, is new as of, I think it's 2 days ago, computer vision. And this is CSCI, I think it's 268 or something like that. I can't remember the course number. And so this is a subject that deals with data, and both 216 DSCI as well as this CS course count towards as a data science 200 level electives. And so this course is purposed with effectively getting computers to see, right? And so you're going to look at different ways of thinking about image data, representation models, the processing algorithms wrapped up in it, and how you computationally characterize the content. And so we're doing some of that, and our tools are things like correlation. In the next 3 weeks, we'll talk about entropy, and we'll look at some machine learning methods. But this course deals specifically with images, because images are a type of data set that's so different, it warrants its own sort of discipline, carving out an area of computer science. And so it's going to be taught on Monday from 6 p.m. to 9 p.m. By a personal friend of mine from grad school who's going to be doing that. He's currently a senior research scientist at iRobot. So he does this stuff in industry, implementing the algorithms to get the Roomba robot vacuum to do what it does. And he was also a computer vision engineer at MathWorks, which makes MATLAB the toolkit that he'll be using for the class. And so he has a lot of internal knowledge of how one of the most popular tools works. So it should be a fun time. The prerequisite, I think, is CS 160. What's that? Algorithms? Is that algorithms? Yes, algorithms. And so it's going to focus on the systems building. There'll be a little bit of math corresponding to things like optimization, gradients or derivatives, and things like that. But the purpose is to get you up and running, building programs, algorithms that do this. And so it should be a really fun class. Okay, so my shameless plugs for my friend Dimitri, Dr. Leeson, as well as my course this fall. Okay, so that's 15 minutes. All right, why don't we jump right in? Any questions? No? All right. So we talked about, to kind of recap all of our discussion about probabilities, both the discrete side as a continued side, we talked about this idea of having a unit of probability mass that's scattered among the support set, all of the values over which the probability is defined. And for the continuous case, we liken that to peanut butter. And with this peanut butter, what the concern is how you spread this thing. It can be spread very thinly, or it can be spread very thickly, or some sort of variation. In this case, down below, we have it going from thin to thick to thin again at a characteristic rate. And we said for the continuous case, we traffic in real valued measurements. And because real valued measurements are uncountably infinite, we can't really take the probability of a particular element from the set of reals over which these probabilities are defined. So the best we can do is talk about the cumulative amount of this unit of peanut butter that is spread over the bread. And calculus gives us some tools, in particular, the definite integral, or the limit case of the Riemannian sum. It gives us tools in order to do that. And so with this, for the continuous case, we traffic in the amount of spread from minus infinity up to some point x. And what the question is being asked by this cumulative distribution function is what proportion of this unit of peanut butter occurs up to this particular point you're calling x. Because one thing we can do with the real number line, we can talk about intervals along the real number line, but we can't talk about individual points because you can't identify them because it's uncountably infinite. Okay, any questions about this? No, jar your memory? All right. And so we talked about distribution families. And these distribution families were developed over hundreds of years, and their purpose was to find functional descriptions for recurring structures for stochastic systems. And the reason for that is because they found, or statisticians over those years, that many systems behave the same. So if you have a functional description, and that functional description corresponds to various categories or families of stochastic behavior, then when you're trying to mimic or model these systems, it switches from all of this deep analysis and proof to matching the structure of these functional descriptions with the behavior of the system you're trying to model. And so we talked about a couple of them. In the discrete case, the Bernoulli distribution corresponds to stochastic systems that traffic in two-way outcomes, and there's a probability or a rate of occurrence associated with each of these two-way outcomes. And so that two-way outcome could be the heads or tails outcome of flipping a coin. It could be picking an ice cream flavor between, say, chocolate and vanilla. As long as the behavior of the system you're trying to study and trying to model matches this behavior of the Bernoulli functional description, then this is a good descriptor, and therefore things like the mean and the variance are useful for describing your system. Does that make sense? Any questions? No? All right. So then we also talked about the binomial, and the binomial talks about a sequence of these two-way outcomes, a sequence of n independent Bernoulli trials. And that independent part is very important because it means that for any trial, the outcome of a trial does not impact the outcome of any other trial among the n many of them. And so if you had, for example, two different coins, and let's say one coin was 50-50 heads, tails, and the other was 60-40 heads, tails. And let's say if you flip the first one, the 50-50, and if it came out heads, you switched to the 60-40. If it came out tails, the next flip would be this 50-50. That is not independent, because in that case, the outcome of one trial it does depend on the outcome of another trial. And so this independent part of the sequence of Bernoulli trials is really, really important to the behavioral description of the system you're enterprising to describe. That dependent one is a different distribution that we're not going to talk about. All right. Any questions? Does that make sense? Yeah. And then for the binomial, they're independent Bernoulli trials, but we also have that success rate P associated with one of the two-way outcomes for each trial, and another rate 1 minus P associated with the other outcome. And so the ask for the binomial distribution is what is the probability, the likelihood, or the rate for which you're going to see X many successes among these N many independent Bernoulli trials. Okay, so any system that behaves that way, and we'll have an example, is well described or modeled by binomial. So then we took this Bernoulli trial again, and we composed another sequence, but this sequence is highly stylized. We have some number of slots, and each slot represents a two-way outcome, but this two-way outcome is particularly stylized. We have a train of failure outcomes ending in a single success outcome. And that's our geometric distribution. So again, we have independent Bernoulli trials, but the schema is different. It's not arbitrary interleaving of these two-way outcomes. It has the failure outcome ending in a single success outcome. So any system that you can model in this fashion is well described or modeled by so-called geometric distribution. All right. Any questions? No? All right. So then we also talked about our negative binomial. And again, this is yet another sequence of trials. But this negative binomial talks about the number of trials in order to get a prescribed set of successes. So you want to know how many times do you have to roll that die, or rather flip that coin, in order to see a number of success outcomes that you desire. And as you can imagine, if the success rate for a single trial is very low probability, it's going to take you a larger number of tries in order to see that K many successes. If the success rate for a single trial is very high, a high probability, it's going to take you fewer. And so this negative binomial is a sequence, but it's a sequence of these stylized Bernoulli trials. It's a sequence of geometric distributions, because each of those K many geometrics ends in a success, and you want to know how many tries for that kth success at the end of the kth geometric distribution. Does that make sense? Any questions? No? And it's called negative binomial, not because of any mathematical relationship to the binomial, but it's called negative binomial because it's asking for a different thing. The number of trials is what you're asking for. With the regular binomial, I won't say non-negative, but with the binomial distribution, you're asking for the number of successes. Here, you say successes, how many trials. With the binomial, It's how many successes, okay, for n trials, which is fixed. Any questions? No? All right. And so for the last of the discrete distributions, we talked about the Poisson, and we said the requirement for the Poisson is that your window of observation, delta t, has to remain a fixed length over time. And it doesn't matter, delta t could be every hour, could be every 5 minutes, it could be every 10 milliseconds, could be every millisecond. It doesn't really matter. And so from this, we calculated an idea of the rate, and we used the limit case for the binomial to talk about the number of events that arrive in time. And so when you model something with a Poisson, what you're asking is what is the probability that given this overall rate, we're going to see some specific number of events in a single window, delta t. And so when you're modeling with a Poisson, what's really important to determine is how fine-grained your representation is. And so you could decide from a data problem, for example, that talks about the number of customers that come into the store, and you could record that data over the course of a 9-hour day, for example, of operations. Now, you could choose to model that entire 9 hours as a single Poisson, or each hour as a Poisson, so you'd have 9 Poissons, or you could model every 5 minutes. It's really up to you. Engineering-wise, the trade-off is a classic one in modeling between specificity and computation. The more fine-grained your model is, the more distributions for each of those hours of operation that you're going to be using, and the more computation required to do that. That's a classic engineering trade-off, but at the end of the day, if you want to have a finer grain, better representation of your system, it's important to decide what level of representation is warranted, right? And so, of course, if you're modeling down to every microsecond, right, 10 to the minus 6, you're going to need a big server to do that. But then the question you should ask yourself, is that necessary for the type of problem you're trying to, for which you're trying to produce an answer? Okay. Any questions? No? All right. We talked about the continuous distributions, and for the continuous distributions, they traffic in real valued quantities, and we no longer have a probability mass function. We have that density function that talks about the proverbial thickness of the peanut butter spread across the support set. We talked about time between events, that's the exponential. Sometimes it's called the inter-arrival time. And this actually follows from the Poisson. It's the amount of time between the next occurrence of an event. Now, Poisson is discrete and has a mass function, but exponential, even though it's related, it's not the same. It's continuous. It has a density function. And so anything that talks about time is well modeled or described by an exponential distribution. The gamma is a sequence of these exponentials, and it's for any type of system that can be represented as a set of alpha many steps, each of which takes some time, governed by parameter lambda. And so this exponential is a sequence of, the gamma is a sequence of exponentials. And you might ask yourself, why don't I just use a single exponential? Well, the reason being is when you have a sequence of independent steps, there's variability, and you can't just represent it well with a single exponential talking about the time that has transpired between when that alpha phase process started and when it ended. You'll never get very good results for that. Okay, any questions? No? And then lastly, we have the normal distribution, our classic bell curve. Sometimes it's called the Gaussian distribution. They're synonyms. And this has a good representation for so-called physical quantities as well as inertial quantities, things that interface with the real world, temperature, position, pressure, etc. And when we said inertial, we said that these physical quantities, they don't just change arbitrarily to values from one observation to the next. The next observation has something to do very strongly with the current observation. Okay, any questions about this? No? All right. And so with the central limit theorem, we said that any distribution, and we'll see some examples today in Jupyter Notebook, any distribution, regardless if it's discrete or continuous, or what the distribution family is, this form, it can be made to look like a normal distribution. And so we take n many measurements and we transform these measurements from any distribution using some operation that involves a sum. And the more terms in that sum, the more and more this transformed version, regardless of distribution, looks like a normal distribution. So that means you can take something that's Poisson, you can take something that's gamma, and you can make them look normal. And now, if you then transform them to a so-called standard normal, does for distributions what percentages do for proportions, now you can make comparisons between systems, even though they traffic in entirely different quantities and they're described by entirely different distribution families. Absolutely beautiful result. Okay. Any questions about this? Does that make sense? And so let's have some examples. And so, I like fishing. I don't think it's boring. It's kind of relaxing. So fly fishing for trout involves an artificial fly, because trout eat flies, that you tie to the end of your fishing line, and then you cast it, sort of throw it out there on the end of a fishing rod, and then you kind of skim it back across the surface of the waterway. And so the trout, and that's a rainbow trout up there on the right, it sees this, thinks it's a fly, and then it goes ahead and bites the fly, trying to eat it. And the hook is inside this artificial fly. You feel it tug on your line and you reel it in. And so suppose in this example, and I'll ask you, there's an 8% chance of catching a fish each time you cast. So you cast it out and then you reel it back in, skimming it on the water. Let's say there's an 8% chance of landing a trout for each cast that you make. And let's imagine then there's a 3-catch limit. A lot of fisheries and wildlife, they limit the amount of fish you can take. And not part of this problem, they also limit the size of the fish that you can take, because you won't want to remove all the young ones from the population, and you don't want to remove all the old ones from the population. You want the middle-aged fish, so to speak, and size is a proxy for age for fishing. And so if there's a 3-catch limit, meaning you catch 3 fish, on average, how many casts are you going to make? And so if you think of that 8% as the probability of, oh, let me let you think about that. I'm not going to go on autopilot. So we have a probability, right? So what distribution do you think would describe this? So you're casting, right? And what are you looking for when you cast? You want to catch a fish, right? Okay. I'm sorry? It's related binomial. What's the probability of having 3 successes catching a fish? But this says how many casts. It's related. Great. Thank you for answering. What do you think? It's related to the binomial. Sounds like binomial, but the ask is different. This is asking for a cast. A cast is a trial, right? So a try. Yes, yes. Yes, the negative binomial, right? And so if your chance of success, P, is 0.08, 8%, it's asking how many times do you try in order to walk away with 3 successes, okay? And so then if you had some data from fisheries and wildlife, and you know that it's going to take a certain amount of casts, you could proxy that to the amount of time that someone's going to spend, and then you could decide to set your catch limit based on the population of fish that you stocked in the waterways. A lot of fisheries and wildlife will actually stock trout and other species of fish in reservoirs. Wachusett Reservoir up by Boylston, West Boylston, is one of them. The Quabbin Reservoir up in Belchertown area in Western Mass. Having fish, freshwater fish in reservoirs is a good proxy for assessment of the health of the waterway. Because if the fish don't thrive, it means the waterway, the reservoir, is not as healthy. Okay, all right, great. So let's take a look at this one. Suppose you have an ice cream party, and let's say the U.S. Dairy Commission collects statistics based on sales of ice cream, and you have 2 flavors of ice cream in this example. I know that's not all the flavors that are in existence, You have chocolate and vanilla. And so let's say we knew that in the United States, chocolate is consumed at twice the rate of vanilla. Okay. So that gives you some rate information and you have to calculate it, right? Because if one is twice the other, you have three parts. That's a 1/3, 2/3 probability, 0.33 and 0.66. Does that make sense? So you have a rate, and let's say you're planning an ice cream party, and this is the rate, and let's say it's for a school, elementary school, and they're going to have an ice cream party. All the kids are very excited about it. And let's say in the school, there are 100 children, okay? But you don't know who likes what. You just know these overall rates. So you want to kind of estimate how many servings of ice cream do you need to buy? Okay. Well, if you have 100 students, let's say you took a survey. You submitted a little paper to each one and said, what ice cream do you like? And so one of the things you might want to know is on average, how many will select chocolate and how many will select vanilla. So we have a two-way outcome, chocolate and vanilla. And, most elementary school students, they don't care what their friend likes. They're going to say what they like, right? And so they're independent choices. We have 100 of them. So now what we want to know is how many are going to be chocolate. And so what do you think? What distribution might model this? So you have a fixed number of tries. Each try is asking someone which one, chocolate or vanilla, which one, chocolate or vanilla. Does the ordering matter about who said chocolate, who said vanilla? It's just some interleaving of these two-way outcomes. So we have a probability associated with chocolate. We have a probability associated with vanilla. That is exactly a binomial distribution. The question is how many of a success, and you can choose to make picking chocolate as your success state or choosing vanilla as your success state. It doesn't matter. So then we know the expectation of our selection, E equals NP. So we have N is 100. P, if that's the probability of chocolate, that's 0.66 times 100. That's 66 children. And we know the variance is NPQ. So if the variance is NPQ, we have 100 times 0.66 times 0.33. And we know that variance, and knowing that variance, take the square root, that's our standard deviation. And we can say, take the mean and go up 2 standard deviations, and that'll tell us on average, what's the most amount of each item we should buy. Does that make sense? Any questions? All right. So again, we're taking a system and we're choosing a functional description among our distribution families that best describe the problem. Okay. And another one, it's hard to come up with these examples, right? Let's say, when I came to Massachusetts, I don't get this whole, I call it a racket for state inspections, right? Every year you do it and you pay money. In Delaware, everything's done at the DMV and it's good for 2 years and they don't bother you. And then when you go in, you go to the counter, you pay, you get your inspection sticker. And if you got a renewed license, they print it right there and give it to you, not this stuff where they send it to the mail like 9 weeks later. But anyways, so a repair shop decided that they want to collect some information and they're going to collect the tire pressure for the cars and they're going to limit that to Honda Accord sedans. Okay. So they're going to collect N measurements. And the question is, what is the best model to represent this? Okay. So is pressure, is it a count? Is it countable? Or is it uncountably infinite? Right? That's the first question. Well, I don't have a pressure of 1, 2, 3. I could have a pressure of 1.532 bars, however many bars of pressure, if bar is the way to measure it. And so this is absolutely real valued. So that eliminates all of the discrete distribution families as the model for this. And it's also inertial, right? If you have a tire pressure, it's not all of a sudden going to quadruple at the next instant, right? Each pressure, if you were to measure it at intervals in time, the future pressure at the next instant is going to have a lot to do with the previous pressure. And so that's a normal distribution. It's a physical quantity, it's inertial, and so we would measure this as Gaussian or normal distribution. And then we could sample from it. We could ask questions. What's the probability of the pressure being in this interval? All sorts of examples. Okay. And so let me ask you this kind of related question. Why did I limit this to Honda Accord sedans? What do you think? Take a guess. Why'd I do that? Yeah, what do you think? Hmm. Hmm. Yes, because it's a different part of the population. If it's a Honda Accord sedan from one Accord to the next, it's the same kind, the same thing. If I had a, I don't know, just pick a car, Tesla or something like that, the tire pressure for Tesla might be recommended to be much greater. And so you can't have a distribution for things for one thing. It has to be kind of the same type of system that you're talking about. And if the system is too different, you're going to introduce two entirely different pressures in your measurements, and it's going to throw off any sort of result you're hoping to have from your modeling. Okay. Any questions? No? And so this idea of distribution families kind of changes the consideration to does the system's behavior match these functional description behaviors? And all of the work has been done for you hundreds of years ago. Okay. Does that make sense? No? Any questions? So with the central limit theorem, and we'll pivot to the Jupyter Notebook, we're going to transform our measurements with and transformation involving a sum, in particular the sample mean, which is the same as summing together some measurements in a window, k many large, and then multiplying each one by a scalar. And so I'll actually show you how that changes the form to look like a normal, and then I'll standardize it and show you the standard normal version. Okay, so let me bring down the slides, and I'll bring up the Jupyter Notebook. Let me redo the share. And sometimes the PowerPoint just kind of roils everything. So close PowerPoint, share the Jupyter Notebook. Let me maximize that. I'll hide the meeting controls. Okay, so, and then as time permits, so we'll have plenty of time. We just might get out very early today. As time permits, I'll also go over question 9A solution to question 9 from written exam 1. So I imported system just because I wanted to figure, I wanted to, brain hiccup. I wanted to get a visual on what version of Python I had, and I can't remember where exactly. I think there was some API I was tinkering with, and it wasn't available in one version of Python, but is in another, and I have a different version on my machine at home versus on my laptop. And so I imported system, and I imported NumPy and PyPlot. And then from SciPy stats, I imported all of the distributions that we talked about, Bernoulli, binomial, geometric, negative binomial, Poisson, and then uniform, which is a continuous one, exponential, gamma, and the normal distribution. And so from that, I start out, and I like to, in this case, print out, why isn't it running? The version of Python that I have. So I'm using 3.9.12. And that was important to me for various reasons, not related to this class in particular. So now I'm going to define a couple constants that I'm going to use just because it's more descriptive. And I have a uniform, I shouldn't say uniform. I have a standard, I shouldn't say standard, standard normal. I have a particular way from each distribution that I produce the samples. And I like to be consistent with that and then make it easy to say, select this type of distribution, select that type of distribution. So I define a bunch of constants so that later on, all I need to do is specify the type that I want, and I only need to change the code in one place. So that's why I define these constants that allow me to select the distribution type. And this is on the, not Moodle, the Canvas site for the module for lab number 9. So I go ahead and I set those. And so the num samples, that's another global variable. That's the number of samples I'm going to take. So 1,000 many times, I'm going to do something. Either I sample from the distribution in its unadulterated form, or I sample a window and compute that transformation on that window of samples, the k-many part. And so either I sample num samples many time, or num samples many time. In this case, I select a sum that's going to involve the sum of 5 samples. And so in the latter case, I collect 5 samples, compute my transformation, then collect 5 samples, compute my transformation, and I do that 1,000 many times, right? So num samples is how many things or measurements that I have, but this sum size, it's the window size involving that transformation. Does that make sense? Any questions? No? All right. So I set the histogram bins because it's a nice thing to do. I don't like to take defaults. I like to control values for things for visualization. And then here in cell 17, that's where I select the distribution type. Right now, it's the Bernoulli distribution. That's the two-way outcome with a probability associated with each one. And so then in the next section, after selecting the type, I have the parameters for all the distributions I can represent or sample from. And so for the Bernoulli, I have the p-value for the Bernoulli. For the binomial, I'm going to set n trials and a success rate of 20%. For the geometric, it's going to have a success rate of 20%. Negative binomial, I want to have 10 successes. And so I want to know how many trials in order to get 10 successes given my success rate of 20%. And then for Poisson, I'm going to set my lambda to 3, and you can set these to arbitrary values of your choosing. For the uniform is a continuous distribution. It's real valued, and it's defined between an interval so that peanut butter is spread evenly between these two intervals, A on the low side and B on the high side. For the exponential, that's the one that traffics in time. The lambda parameter is 6. And then for the gamma distribution, we have alpha, 8 many steps, each one governed by an exponential with lambda parameter 6. Does that make sense so far? Yeah, all right. And then for the normal distribution, mu, the mean, is 15, and sigma squared is 25, so that means the square root of it, the standard deviation is going to be 5. And so you can set these to whatever. For the real valued ones, you don't have to have it. Well, for the normal, your values can be decimals if you choose, but I've just chosen these values. Okay, so we set all the parameters for all the distributions we're going to consider. And then in cell 19, these are what I call the central limit theorem version of my data points. And so we said num samples in this case is 1,000. So 1,000 times I'm going to compute a measurement, but this measurement is going to be the mean of a set of samples k many y. And so I set this CLT array for each one of my distributions, and then I have some others for collecting samples. And so in this next section, I have the different types of distributions, and in each case, I have the sampling from the random variate sampling API in SciPy, in the SciPy module for each one of these distributions. And I give them the parameters. Since this is a Bernoulli, I give it the Bernoulli P, and then the size, the number of samples, is none samples, many samples. For the CLT version, I select a window of observations. Here, I call it Bernoulli window, and I select sum size. These are the number of terms that I'm going to transform. And so in that case, my measurement is not a single sample. In this case, it's the mean of some many terms. Does that make sense? Any questions? All right. And so what I'm reporting is a measurement. That measurement could be direct sample from the distribution, or it could be the transformed window of observations over which I take the mean. And so I call it the samples, which are the untransformed samples, 1,000 of them. And then I have the samples CLT, Central Limit Theorem, which is the transformed version of the samples, where each measurement here is the mean of some number of samples. Okay. So I do that for the Bernoulli. I do that same thing for the binomial. I do that same thing for the geometric, the same thing for the negative binomial, as well as the Poisson and the uniform, exponential, the gamma, same thing. I say gamma, random variate sample. I give it the parameters of the gamma, alpha and lambda, num samples, many samples. In the case of the CLT version, here's my window. I take some size, and I compute the mean, and the measurement that I'm reporting is the mean of some window of observations. So I'm consistent in that, and what each block in this sequence of if, else if, else if, else if statements does, it just selects based on the distribution type, which particular distribution I'm going to either produce the untransformed samples or the measurement, which is the mean of a window of samples. Does that make sense? Okay. So then I come down here. So let me execute that cell. Oops. Oh, you know what? I did not. Let me do. All right. There we go. All right. So now I take the samples, and right now my distribution type is set to binomial, and I go ahead and I plot a histogram to visualize the distribution of to visualize the distribution from which I've made unmodified or untransformed samples. And like any binomial, I see two bars, and the size of those bars represents the rate of failure and the rate of success. The success rate was 0.2. We see this bar on the right. It's at success, which is 1, and failure is 0. And we have 200 of the successes out of the 1,000 samples, and we have 800 of the failures out of the 1,000 samples. And yes, absolutely, that represents the 0.2, 0.8 success rate and failure rate. Any questions? Does that make sense? Yep. And so now let's look at the sample CLT. These are 1,000 means sampled from a window of, I think it was 10 observations. And so here, let's visualize that one. You'll notice it doesn't look like a binomial. If you were to kind of draw the envelope, it kind of almost looks like a normal distribution. And what you'll find as you increase the window size over which you compute the mean, and as you increase the number of samples, it's going to look more and more like a normal distribution, even though underlying the individual samples are from a Bernoulli distribution. Does that make sense? All right. So let's go ahead, and now for each one of these means, we're going to standardize it to make it into a standard normal distribution. The first thing we're going to do is compute the mean of each one of these means, and then we're going to compute the standard deviation, sometimes called the standard error. Anytime you have the standard deviation of a statistic, a function, and the mean is a function, it's often termed the standard error, just as a note or a nod to say, hey, there's something different about this standard deviation. It's not just a raw measurement, it's some statistics standard deviation. So we compute the mean and the standard deviation of the CLT version, which is the transformed version of a window of K observations. And then we're going to go ahead and we're going to subtract from my measurements the mean from each one. And then we're going to multiply by 1 upon the standard deviation, which is exactly what transform into the Z distribution prescribes. So we do that computation, and now we're going to compute the histogram of that result, which we call CLT Z distribution version. So we go ahead, compute that histogram, and you'll notice here, we have a similar shape here, and it gets more and more looking like a normal as we increase the number of samples, increase the window size. But you'll notice here, the mean is right around 0.3 or so, 0.25. If we go to the CLT Z version, you'll notice the mean, the center, is right over 0. And if we go to the left and to the right, like 1 to 2 standard deviations, we get most of the probability mass. Does that make sense? Okay. Any questions? So what if you said, Holness, I don't believe you? Okay, that's a good point. So we have a window of 5 observations, and we have 1,000 samples. Let's bump it up to 20 observations, and let's see how that changes. I wish I had something to preserve the other graph. So I'm going to rerun from that cell where we change those parameters, and we're going to keep it as a Bernoulli distribution. And here, well, that hasn't changed. It's the 20%, 80%. We're going to do the CLT version. That's the mean. And guess what? Look, it looks even more and more normal. We didn't change the 1,000 many samples. All we changed is the window from 5 to 20, right? 4-fold. And we notice it looks more and more like a normal distribution. Looks nothing like a Bernoulli distribution. Let's go ahead and center it using our Z distribution transformation. And we'll notice here, if we scroll down, guess what? 0 is the mean. We go 2 standard deviations to the left and to the right, most of the probability mass. And this is a standard normal distribution. One of the things in Python, it tries to make your graphs look pretty. And so it tries to keep the scale big. But if I fix the scale, you'd actually see for the second version, this is actually kind of scrunched in more because it's a standard normal. It just wants you to make it look nice, so it makes them the same width. But in truth, if you look at between -2 and +2, we have most of the probability mass centered around 0. Between -2, +2, it's going to be a little bit different because you see the numbers along the horizontal axis are different. Does that make sense? All right. So, okay. Well, let's try this out with a different distribution. Let's try this out. Go back to some size, a window of 5 observations over which we compute our transformation, and let's do the exponential distribution. That's a continuous distribution. We just did the binomial, which is discrete, right? So let's save that. And just for good measure, I'm going to re-import the libraries. Now it's a window of 5 observations, and we're going to take 1,000 such measurements. Histogram bins is still 20, and we're doing the exponential. So the exponential, it has a lambda, okay? And we're going to set those data structures, and we're going to do our sampling. So now let's plot the exponential distribution, and you notice it's an exponential decay. That's the characteristic shape of the exponential. And if you change lambda, what it does is it shifts what's called the elbow of the graph, either further out to the right or further in towards origin. So it's a classic exponential, okay? Let's do the visualization of the CLT version. So now we're reporting a measurement is the mean of a window of 5 observations. And guess what? Here, unmodified, we have a decaying exponential. And this is starting to look more and more like a normal. We can transform it to the Z distribution. And when we do that, we notice it's centered about 0. And if you go plus or minus 2 standard deviations, plus or minus 2, it's most of the probability mass. All right. Well, let's try this out again. Instead of a window of 5 observations, we're only going to change it to a window of 20 observations. It's still the exponential. And when we do that, well, okay, we get that decaying exponential. When we look at the CLT version, it's getting more and more like a normal distribution. It's not quite as lopsided as it was before. And again, we do the Z version. And of course, it's centered around 0. And it's sort of shrunken down so that plus or minus 2 standard deviations about origin, it's most of the probability mass. And so whether it's the exponential, binomial, Bernoulli, it doesn't matter, continuous or discrete. As long as your transformation involves an average, you can make any distribution look like a normal distribution. So yes, the central limit theorem does work, and it's a wonderful tool that, along with the transformation to Z distribution, so-called standardization of your measurements, you can now make with this Z version measurements like correlation and fair measurements between 2 different systems, regardless of the structure of the stochasticity of those systems. Does that make sense? Any questions? Yes, yes. Mm-hmm. Mm-hmm. So here, I have the sample CLT, and this is just in my implementation, right? This is not like, this is the way you should do it, right? Hope I didn't suggest that or make it sound like that. So the sample CLT, each measurement or each measurement in this array, the sample CLT, is where I'm placing the mean of a set of 20 measurements from each distribution. And so 1,000 times, I'm taking a window of 20 measurements, computing the mean of that. And that each such measurement is inside of this array, the sample CLT. So I take the average mean. Does that make sense? The average mean. And then I also take the standard deviation of all of my means. And then from that, I first take each mean and I subtract the average of the means. And then with that result, I CLT centered, I multiply by 1 over the standard deviation of the means. That's the same as dividing by the standard deviation of the means. So now the result I'm calling my Z-scores, and each Z-score is the result of first subtracting the mean of each measurement and then multiplying that result by 1 upon the standard deviation of all my measurements. And so you could convert from z-score back to the original measurement. I think I have the math in a slide, but I don't do that here. Okay. Any other questions? No? All right. So I would encourage you to tinker around with this. If you're visual or data driven, it doesn't matter what you use or how complex the original distribution is. That's only going to impact the number of the size of the window that you use. Okay. And as we see here, as you increase the size of the window, it gets more and more and more like a normal distribution, regardless of what the original distribution started out as. Okay. Any questions? No? All right. So we have about 17 minutes. So let's pivot to question number 9 from written exam 1. Now, I stress this is a model solution, but not the model solution. There are a lot of different ways one could do this. And there were a lot of very clever things that people did. I was very, very happy about seeing that. When you think about a decade of age, it's an interval. And with this interval, you could choose to iterate through all the ages sliced out of the Titanic data set, and then check them against the different decades, and then assign them to a new column. There was one example where somebody very cleverly used the floor function in math. Floor overrides the default rounding rules. And so what floor says is, say, if you're a number and your number is between 2 values, it says round it down to the next integer value, but then you could do that down on a decade boundary as well as just an integer boundary. So I thought that was very clever what someone did. But nonetheless, when we talk about decade of age, the approach I used for the data cleaning was to replace the not a number entries for age, and there were quite a few of them, with the mean. Now you could choose to drop those records. You could choose to set them to 0. You could choose to replace with the mean. Now, I've chosen to replace it with the mean because it's what I call statistically neutral, right? You don't change the central tendency when you replace things with the mean, but it does overrepresent those who are corresponding to that bin, that decade, that are right in the middle, right? So there are trade-offs, and that's the trade-off that I made. Now, in terms of testing for the relationship, there were some that took what was called a stratified version of the data set. To stratify means to partition something into layers, where membership in a layer corresponds to some criterion. And so in some cases, with this solution for question 9, people partition the data set based on age. And then when you got those individuals in a particular partition, then filtered through and said, okay, what is the rate of survival? And then they plotted either as a graph or a bar chart, the survival rate and the non-survival rate or rate of perish for each of those age groups. And so I've chosen to do it as a conditional probability, which is effectively stratification. When you have a condition given a decade of life, it's a so-called filtering probability, as we discussed. So I set aside those that are in that decade of life, and then I evaluate the probability of survival equals true, and the probability of survival equals false. And so it didn't really matter what approach you used. What mattered is that you observed this idea of partitioning in terms of age in some fashion, and then you looked at the survival rate and show that the survival rate changes in some fashion as a result of each one of these subgroups corresponding to those of a particular decade of age. So that was the important part. The consideration, the recognition of stratification, and then the method of visualization, and not so much this particular choice you made, but that you recognized these things. Okay, any questions? No? All right. And so in this solution, we import, and I select age bins to be 8 because you have ages from 0 to 80. And so in my mind, that represented 8 different decades of life. And so I define strings for the decades, and I make this an interval, and I think this description is wrong. It should be the other way. No, that's right. That's right. It's a so-called half-open interval. And in a half-open interval, um, well, if you have a number line, and let's say that's 1 and that's 10, this is a closed interval, and a closed interval mathematically is represented as a square brace, 1 comma 10. And if you have an open interval is everything in between, but not including the endpoints, right? And with an open interval, you have the parentheses. Hopefully I'm getting this right. And then you can have a half open interval. Half open interval can be open on the right, or it could be open on the left, right? And so the dot means it's closed, it includes the endpoint. The circle means it's open. And so in the first case, you'd have closed on the low end. If this is 1, this is 10, this is 1, this is 10. You'd have closed on the low end here, 1, and open on the high end, 10. And conversely, you'd have open on the low end and closed on the high end, 10. And so one of the ways you can partition is there's an API call called the cut API. And what cut does, it allows you to specify boundaries, but you specify whether the left should be open or closed, or the right should be open or closed when you define these boundaries. And so first, any questions? Does that make sense? No? And so I defined some strings just because it's nice to have more descriptive variables to talk about stuff. And then I construct an array of these decade strings. And so I called 0 to 10 half open, call that the ones decade, and then the tens, or you could call it the teens if you wanted to, 20s, 30s, 40s, 50s, 60s, 70s, etc. I construct an array for that, and then I set survivals because I thought I might need it. I go ahead, I read in the CSV file, Titanic CSV, as a data frame, and then I just take a look at it because that's always a nice thing to do. So then I slice out 2 of the columns that I need, the survived column and the age column, because my transformation, my analysis is only going to involve them. And then I go ahead and I plot them out because it's kind of nice to see them. And then after that, I calculate how many of my ages are not a number. And so I slice out of the survival age version, the age series or column, and I call is not a number, which returns true and false, or false. And I take advantage of the fact that underneath the covers, a true is a 1, even though it's a Boolean, and a false is a 0. So I sum together all of them, and it gives me a count of the number of entries that are not a number, and then I just put that out in a formatted string. And so now I say, okay, is there any not a number for the survived? Even though survived is a true false, there might be a not a number entry. So I do the same thing, is not on the survived slice, gives me a series, which is the column implementation, and I compute the sum of those true false values, and there are no such entries. So at this juncture, I know I have 177 entries out of the total 800 some odd entries that are not a number for the age value. So I need to do something with them. First, any questions? No? Make sense? No? All right. So then I go ahead and I compute the mean of the age slice, and I can kind of get away with that because when you compute the mean, it's going to skip over entries that are not a number. So it's not going to be included. So I take all the mean over all of the I don't like to use negative logic, on the not a number, on the existing entries in age, I compute the mean of them. And then I go ahead and I do that replacement of everything that's not a number with the mean. Now, one of the ways you can do that is you can define what I call fill values. And this is in a dictionary. And we have as the key value the name of the column or the key for the data frame. And then the value associated with that name is going to be the value you're going to use to do the replacement. So here I'm saying if you are not a number for the survived column, replace that with 0, which is false. So I could have just spelled out false. But I know there aren't any survived entries that are not a number. So it doesn't really matter what you call that. I just gave it a value because I also wanted to show you this more sophisticated replacement approach. And then it says everywhere you see age, if it's not a number, replace it with mu age, which is the mean of the existing values. Does that make sense? Okay. So then I go ahead and I say, go ahead and fill, not a number, value is fill vals. And with specificity, it's going to go to each one of the columns in the data frame and do the replacement of not a number entries with whatever this mapping was that I specified. Okay. Any questions? All right. So let's go over that. And so now, just to kind of close the loop and verify that it did what I thought it did, I recalculated how many of these ages were not a number, and now none of the entries were not a number. Okay. Does that make sense? So you always sort of, what they say in the Army, trust but verify, right? You always want to verify because it's just kind of nice to do so. All right, so then the next thing I do, I want to look at my ages because I know that the minimum age, I get the minimum, get the maximum, and I print that out. And because 80 is the maximum, I asked myself, how significant is this population of people? Yes, every person matters, every life is precious. But I just want to know data-wise how many of this population is represented by the age group in the decade of the 80s. So I actually count how many are of age 80, which is the maximum. So I go ahead and I filter out by age those records in that slice, in that series, that column for age, how many equal to 80. And the matches gives me a result of true, false, and true is also mapped to 1. So I just sum them together. And it says that I only have one person who's of age 80. So when I do my analysis, I say, you know what? Out of the 800 some odd people, I've replaced 177 of the not a numbers with the mean. This one person who's 80, it's not going to make much of a difference on my analysis. So I'm just going to exclude that from my consideration. That's also for convenience, because if you notice here, I have a half open intervals when I talk about decade of life. And so here, the decade of the 70s starts at 70, but it doesn't include 80 because it's a half open, where it's open on the high side. Does that make sense? So I made the concerted or deliberate decision not to include that single 80-year-old person for the analysis. Okay, so let's go back down. We did some of that. Okay, min max, one person who's 80. And so now I go ahead and I compute a histogram using 8 bins because there are a total of 8 decades. And if I use 8 bins, given my span from 0 to 80, it's going to be roughly every decade if I specify 8 bins. And so I go ahead and I do that histogram just to get a quick sense of what my data looks like. And I have 4 more minutes. I don't know why I did that, to show me what the histogram's object name is. The next thing I'm going to do is I define bin edges. I know that the ages are each decade, 0 to the 9 version of the age, so 0 to 9, 10 to 19, etc. And so I go ahead and I construct the bin edges that define the boundaries for each decade of age. And so this is a step. It's almost like saying range, but you can define what the step size is when you say NP arrange. So it gives me this array, 0, 10, 20, etc. And these are going to be the bin edges defining the lower part and the higher boundary for that interval for each decade of life. So now I go to my data frame and I'm going to use the cut API on in Pandas. And so I give it the array of bin edges, and this is where I control these 2 parameters, include lowest and right equals false. That's where I define whether it's an open interval, closed interval, half open on the high side, half open on the low side. And so here I say, okay, well, I have ages, all right? I have my bin edges. I'm going to cut ages using the boundaries for this bin edges array. And so include the lowest means the left-hand side is going to be a closed interval, going to be the square bracket, including the left-hand side. And the right-hand side, that next option, right equals false, exclude the right-hand edge of the bin. So it's going to be open on the high side. So I go ahead and do that cut, and it gives me back two things. It gives me the representation of the interval, and it also gives me the values, the number of values that fall into these bins. Does that make sense? All right. So now I go ahead and I say, okay, well, go ahead and give me the counts, the number of values in each one of these bins as defined as half open on the high side, and sort them based on the index. And the index is a string representation of that interval, which is half open. Does that make sense? Any questions? No? All right. And so I go ahead, plot it as a bar chart, and I get this neat bar chart. It's in sorted order. There's 0 to 10, 10 to 20, 20 to 30, etc. And along the horizontal axis, the vertical axis is the number of counts. And as you can see, the decade of the 20s, that seems to be the largest count among the population from this Titanic data set. And so sometimes it's useful to be reminded what the type is. And then I go ahead and I take the index itself, which are these intervals. They start out as intervals, and they're not strings at that moment. So I decide, go ahead and convert them to strings, okay? And then I print it out to kind of remind myself what these strings actually look like. Just because it looks like a string, it doesn't mean it is a string. You can only print it if it is a string, all right? Does that make sense? Yeah, all right. So now, excuse me, I want to record how many passengers I have, and I kind of use the shape variable to do that. It's an array that tells you the number of rows and number of columns, and the number of rows, which is in the 0th position of shape, tells me how many records I have, and these are the number of passengers. So then I go ahead and get the age array. All right. And this is sort of a nod to this stratification, right? So I start out and I go through the age array, and I go ahead and I want to build a new column by taking an array of a decade representation. I already said convert it to a string in this cell, AS type string for the index. But down here, I decided to go ahead and calculate it by hand because I saw so many examples of people doing it by hand. So I go ahead and I loop, and I have this thing called decades. Decades, if we go up top here, decades, excuse me, had these strings in order of decade. And so I loop through all of the age boundaries, 0, 10, etc. And I set the left edge and I set the right edge from that array of edges. And then I go ahead and check each age against these bins. Here on the left-hand side, I say greater than equal to, it's closed. Here I say less than, it's open on the high side. And so now when I know what bin a particular age falls into, I say go ahead and append from the decades array that string representation for that particular decade this age falls into. Does that make sense? All right. So now once I do that, I just remind myself what it is, and I go ahead and I construct a series from that new array of decade strings, and I go ahead and create a new column in the data frame that I call decade. All right, all of that just to create a new column. But I saw people partitioning by hand and wanted to show you an example of doing that. Okay, ooh, we're right on time. All right, let me take 30 seconds to finish this. So then after that, I have this routine we had covered in a different practical section for computing conditional probability. You set the universe of consideration, do your filtering, and then compute the favorables. And so here, I test it out because I just want to test it out. I have the probability of A given B. So A, the variable, its value, given the second variable, its value. And then I give it the universe, which is all of the records. And then quiet just says, do you print out the visualization of the conditional probability? So that's my example. So now I'm going to go through all the survivals and I'm go through all the decades, and I compute these conditional probabilities, visualizing each one. So if you'll notice here, we have survive equals true, the first few. And then for each survive equals true, I say given the decade, given the ones decade, the 20s, the 30s, the 40s, etc. And we notice survival rate as we condition on the decade. As the decade increases, they get older, you'll notice the survival rate, probability of survival goes down. right? As you get older, your survival goes down. Likewise, if survival is false, we start with the younger, go to the older decades, the survival rate, the perish rate increases. So as you get older, you don't survive. Now, I have a description of the result, and this is all on the Canvas site. And at the time, they said, women and children first. So it makes sense that children would be, you know, would be highly represented in survival at the younger ages. And then at that time, the you know the families had children at younger ages, and so that would favor also the younger parents at the time, which was in the I think it was 1910, 1920s or something like that. I can't remember the exact date. And so that's an example, and we'll end there abruptly because I'm already over by about 3 minutes. I just wanted to finish this thought. And so it is an example, not the example, and I hope this is all helpful to you. So we'll end there, and we'll pick back up on Friday. Apologize for going over by a couple minutes. I'll see you all on Friday.